Let's discuss how we get a relation between the length of the arc, the central angle, and the radius. So basically, we are considering the arc length, okay, area of the sector, the central angle theta. Do you know the subtended angle at the center? That angle is what we call as theta. All right. So here, let's start with this very simple concept. For this, we'll start with a circle. Imagine we are going to have a circle. All right. Now, for this circle, we have the center. Say center is O. All right. Now, for this particular circle, whatever the center we have, from here you draw a line. Say this is A. Radius. Let's call the radius as R. So, R is equal to the radius. Now, what we'll do, we'll take some angle theta. Again, I'm not specifying it to be one radian. It can be any angle theta, provided theta should be in radian and not in degree. Let me repeat it. Theta, the central angle, has to be in radian and not in degree. Okay, this is the only condition. That means, say we are going to look at some point B here. See this arc length AB. So arc length AB, let's call it as L, or you can say SL, it's up to you. Then we'll join OB. So from here to here, OB. That means here, the angle what it subtends here, let's call it as theta. Alright. Now, the relation between the arc length L, the central angle theta. Think about it. More the value of theta, more is the value of L, and vice versa, correct? That means they are directly proportional to each other. Now, what we can tell is L is proportional to theta, correct? But L is inversely proportional to R. Now, I want you to pause, think about it for a minute. See, I'm telling you that L, the arc length is inversely proportional to R. You can pause, think about it for a moment. Now, why L is inversely proportional to R? Suppose, say, the value of, say, theta is 30 degree. Let's make it constant. Okay. Now, if my radius is, say, 1 centimeter, you will get some value of L. Now, imagine if my radius is, let's say, 1 kilometer. Now, think about it. See the value of L. Just compare the value of L. We understood L is proportional to theta. Now, L is also proportional to R. That means more the value of R, more is the value of L. Okay, now with this particular, relation, what we get is we get L is equal to R into theta. Okay, L is equal to R into theta. Or in other words, we can tell that theta is equal to L divided by R. Now, this is one relation what we can use. Theta is equal to L by R. Or L is equal to R theta. This is also true. Fair enough? Now, the next part what you have to understand is this area of this particular sector. See this area. Suppose if I need to find the area of this particular sector, then again we have a formula. We use A, capital letter A is the area. A is equal to half R square theta. This is the area of cross section. Sorry, not cross section, area of the sector you can say. Alright. Now remember, L is equal to R theta. This gives the relation between the length of the arc, the central angle theta, which is in radian, and the radius. A is equal to half R square theta gives a relation between area of the sector, the radius, and the central angle theta, which is in radian. Suppose if theta is given in terms of degree, assume we have to convert into radian. Now in the last video, we have done the conversion, theta degree to radian and radian to degree. So use that conversion, convert into radian, and only then you will be able to use these two formulas. Clear? So this particular two formulas, whatever you have seen, this gives a relation. Clear? Now in the next video, we'll solve problems based on whatever the topics we have covered so far. Okay, so in the next video, we'll solve the problems.